Okay, in this video I'm going to demonstrate path analysis using AMOS, where essentially what we're going to do is we have a set of measured variables or manifest variables, and we're going to first estimate the path coefficients using this configuration right here, and then what we're going to do is we are going to adjust the path coefficients for measurement unreliability. So the demonstration actually comes from a presentation in this article right here on grit, basic need satisfaction, and subjective well-being. And this article was published in Journal of Individual Differences in 2017. So in this particular article, they examined relationships between these variables, but you'll notice that the authors have each of their factors as latent variables, and then they have a set of indicator variables for each factor. So this is a full structural equation model uh, with paths between latent variables. So unlike this particular study, though, we are going to utilize manifest variables, which essentially are representing composite scores from a set of subscales from the study. Now, keep in mind that one reason why we might choose this option right here to utilize multiple indicators of a latent variable is that it allows us to take into account measurement error when estimating our factors. And so when we generate our model, the path coefficients essentially are adjusted for measurement error. And in this particular case right here, where we have just a set of manifest variables, in this case, when we estimate the path coefficients, one of the downsides is that those estimations are operating under the assumption that we've measured our manifest variables with perfect reliability. So in other words, we have perfect consistency in measurement for the constructs that we're trying to get at. And the reality of the situation is that it's very unlikely we're going to ever, well, we will never have perfect reliability, and there will always be a certain amount of random measurement error associated with any measure that we utilize. Obviously, the less measurement error associated with your manifest variables, the better. And if you happen to have a model that has lower levels of measurement error, or at least random measurement error, then you're going to probably do a better job when it comes to estimating the path coefficients and doing a better job of estimating population parameters. In those cases where you have more substantial levels of measurement error associated with your variables, then what that oftentimes can lead to is an attenuation of the relationships that are being estimated in the model. So in other words, there becomes sort of a bias or a downward bias in terms of estimating those relationships. So you can end up underestimating population parameters systematically as a result of large amounts of measurement error in your model. So that is actually one reason why the latent variable approach that these authors utilize can be valuable. And I will say that in this particular study right here, the indicators are actually they actually form them through a process called parceling, and we're not going to really utilize that approach, but I did want to highlight that it's not always the case that we necessarily want to estimate a full model in this kind of way. And one of the reasons why is that you actually have two kind of components of this model. You have a measurement model component, and then you have the structural portion. The measurement component is relating your manifest indicators to latent variables, and then the structural portion is all of these other arrows that are relating the latent variables together. And if you're using scales that have a lot of indicators associated with them, then you have to keep in mind that you are essentially estimating measurement errors for every indicator that's in your model. Okay, so what that can translate into, that translates into a larger number of parameters that are being estimated. And what happens is that even if you do a fairly good job of measuring your constructs, in general, the measurement errors sort of build up, and so it can kind of contribute to a model that doesn't necessarily look like it's very well specified. So one thing that we might find ourselves doing is trying to sort of whittle down the indicators to a smaller set and use those as indicators of the latent variable. And that's essentially what these authors utilized in this case, where they utilized a process called item parceling, where essentially we might have, let's say we have a measure of grit that has 10 items. Let's just say for argument it has 10 items. I don't really know. But in this case, they could have taken some of the items and formed one composite, another set of items that reflects another, and then another. And so then we would have a parcel for each of those, which might be represented right here. There is another alternative, though, that we can adopt, and that is essentially utilizing the reliability estimates associated with our scales, and then building that into the model and helping to kind of, so instead of using multiple parcels like we might in this particular case, we could essentially utilize the composite measure, but essentially build in a component for measurement error that and essentially build off of the reliability information that we can obtain from our data. So I'm going to show you how you can do this, and so we're going to start off with this particular situation right here. Also note that another reason why I'm not utilizing the parcels, as you see right here, is because I only have data available, the summary data in terms of the correlations among the sums or composite scales, the mean, standard deviations for those scales, and the reliabilities for the scales. So if I had had a matrix of the indicator variables that were reflecting the parcels, I probably would have utilized that instead. But in this particular case, I don't. So I only have the composite measures, but I can still work with this in running my analysis. And I am going to use essentially a path model with the manifest variables, as you see right here. So also one last thing is to say that you can see there are a lot of paths in this particular model in the structural portion, and I'm just taking a subset in this particular case. So as you can see, I essentially have the data in an SPSS file, the summary data. So you can see that I've got the correlation matrix is presented right here. I've got the mean, standard deviations, and sample sizes for the variables as well. And so I'm going to import this into AMOS and then run my basic model first, and then we'll run a model with latent variables and adjusting the measurement errors as a point of comparison. So this is the basic model right here. So essentially, if I was importing the data, here it is, and it's 455 cases. I've got it laid out in terms of the standardized estimate, squared multiple correlations being estimated. I'll click on Calculate Estimates, and when I go over here, click on this button, you can see I've got standard, unstandardized, and standardized estimates for the model. So looking at the output file, I've just clicked on this little view text right here and go to model fit. You can see that the chi-square goodness of fit test is non-significant, so that's consistent with a good fit. The CFI is and TLI are close to 1, as really all of these. You can see the GFI and AGFI are high, and then we can scroll down and we can see the RMSEA is 0.048, which is consistent with a reasonably close fitting model. So just kind of note a couple of things, because I'm going to use this as a point of comparison, which is this path right here. The unstandardized path coefficient has is 0.54, and for this one it is 0.65. So so just letting you know that. Also note that when you look at the estimates right here, you can see that the path from autonomy to life satisfaction is not significant in the model. These are the unstandardized path coefficients. These are the unstandardized estimates. your standard errors, critical ratios, and p-values. Standardized weights are right here. Kind of scrolling down a little bit further, you can see that we have correlations. So we added correlated errors. So these are the correlations between the error terms. And then in terms of the squared multiple correlations, basically the R-square values, you can see that we're doing a pretty good job of accounting for variation in the endogenous variables within the model. So, like I said, the one downside of utilizing this strategy where we have just the manifest variables is that the paths are estimated as if we had perfect measurement reliability, and that's not oftentimes. This is generally not a tenable way of looking at it, or it's not a tenable assumption. Probably it's less relevant or important in those cases where you have high levels of reliability. Then the level of underestimation will be a little bit lower, but if you have a large amount of measurement error associated with your variables, then in that case, then you can have much more substantial biasing of the parameter estimates. So as a point of comparison, what I'm going to do is I'm going to pull up another model, and so this is the comparison model that I'm going to show you here. And I'm going to drag it over just a bit. And as you're looking at this, you can see that we have essentially the same model specification, but instead of using just the manifest indicators, we have latent variables with a single indicator, which is the composite scale for grit, for autonomy, and so forth. So essentially, you can see that we have, it looks very similar to this layout, except that instead of having 3 or 4 or 5 indicators, we only have 1. And the basic idea is that so we still have a measurement model associated with this model, which is the latent variable in relation to their respective indicators, and we also have the measurement error denoted as well. So this is the measurement error associated with grit, measurement error associated with autonomy, and so forth. So the way that this model is laid out basically utilizes a strategy where we essentially compute the variance of a given measure, composite measure. Let's say we sum up or average the scores on grit across the items in the scale, and then compute the variance for the items in the scale. And so when we do that, we can essentially take the variance and divide it out or split it out into a measurement error portion, and then portion that is reflecting essentially systematic measurement of the construct. So the general strategy essentially involves estimating the variance for the measurement, the portion of the variance in grit that's attributable to measurement error, and then the remaining portion is assigned to the latent variable. So that's the basic idea. So the way that we do this is, and I'll show you just kind of a quick little thing here, is that we can estimate the measurement error for a given indicator variable by taking 1 minus the reliability coefficient. So if we use Cronbach's alpha, we would take 1 minus Cronbach's alpha for the set of items and multiply that against the variance of your variable. So, and this strategy is essentially taken from presentation by Schumacher and Lomax in their Beginner's Guide to Structural Equation Modeling. That's kind of where it's coming from. So the basic idea in this particular case, and I'll show you quickly how to draw this out. So I'll start off by just drawing out, and I'm just going to illustrate one of these because obviously this can take a while. So I've just drawn out a box that represents a measured variable. And next what I'll do is I'll go to the variables list here, and I'll bring grit down to that box. And then if I click on this button right here, it says add a unique variable to an existing variable. So I'm going to click on that and click here. And so now I've got essentially a uniqueness that is being specified. So then I just, and then for the next part is I'm going to draw my little oval down below and a line or an arrow from the latent variable to the indicator, which is the composite grit measure. Next up, I'm going to right-click Object Properties, and let me do this again. Right-click Object Properties, and I'm going to fix this particular path to 1, so you can see it's appearing here. So I've got the path from the measurement error to grit set at 1 or fixed at 1, and then the path from the latent variable to grit as fixed to 1. Next, I'll click on the little latent variable and then go to text, and I'm going to just type in a name. So I'll just call this grit1. I'm just reproducing what I kind of have done up here. So then the next step is just basically I'm going to name this. So I'm just going to call this the same name that I did above. I'm just kind of walking you through some of the steps. And then now I have to fix the error variance term. So the way that I do this is I'm going to click on parameters, and you'll see it says variance. And so what I'm going to do is I'm going to put a number in here that represents an estimate of the measurement error associated with this particular scale. So the way that this works is, or the best approach to doing this is essentially go into your, either into your data set, or in this case we have it in the article as well. It's right down here. So we have the Cronbach's alpha for the scale. So that's our reliability coefficient. So if I take 1 minus the 0.8, obviously that's going to get me 0.2, which is reflecting essentially an indicator of the amount of variation, measurement error associated with the scale. And so then I'm going to multiply 0.2 times the estimated variance within the sample for that particular measure. So you can see that we have, let me just kind of go up here for a second, we have the standard deviation for grit, which is 0.51. So if you kind of go back to your initial stat class, thinking about the relationship between the variance and standard deviation, the standard deviation is the square root of the variance. So if I just square the standard deviation that's printed here, then that gets me 0.26. So in a nutshell, if I take the 0.26 and multiply it by 0.20, then it gets me 0.052, and so that's what I essentially typed in right here, and that's how I got that number. So basically then I'll just type in 0.052, and there you go. And so now we've got I've just reproduced down here what I just done above. So if you follow that same general strategy for each of your measures, then you will then have you'll essentially be measuring each latent variable. So the variance in the latent variable will reflect the systematic variance associated with the measurement of the construct, and then the errors are capturing the measurement error portion of the variance in terms of the measure. So that's essentially how it works. So now that I've done this, and I've literally walked through the entire, I did the same process throughout. So just as a little bit friendly reminder, just keep in mind that we're just taking 1 minus the Cronbach's alpha for your measure, and then multiplying that difference by the variance of x. So if you have to do it, because a lot of times articles are printed out in this kind of way with just the standard deviation, then it would just be the 1 minus Cronbach's alpha times essentially your standard deviation, which is squared. So and that's basically your variance. So at any rate, so you do that for each one of these, and now let's compare our results. So at this point, I'm going to by the way, just one other point. This, this path, needs to have a fixed coefficient of 1, and then this path needs to have a fixed coefficient of 1. So make sure that you have laid out your path coefficients with their fixed values of 1, or else you're going to run into problems estimating. So now I'm going to run the same model. I've got the data in here. I'm going to go under analysis properties. You see everything's the same. I'll click on calculate estimates, and now when you look at the coefficients, remember that previously the unstandardized path coefficient for grit to autonomy was 0.54. Now it's a 0.68. So we've corrected the measurement of grit for the unreliability in measurement, and so then we now have a path coefficient that is doing a better job of estimating the population coefficient. This path from grit to competence here, you can see it's now 0.8, whereas previously it was 0.65. So you can see by way of comparison that we are improving our estimates of the path coefficients by essentially addressing that issue of measurement error, building it into the model. And that's all that we're basically doing when we utilize a latent variable model such as this. It's just that since we're only using a single indicator as opposed to multiple indicators, we have to kind of come up with a little bit of an indirect way of reflecting the measurement error. And so that's the strategy that's been adopted. If we go and we look at the model fit, you can see that the end result was that the model still appears to be fitting. We see that the goodness of fit test is still non-significant. We see that all these values are well, quite high, and you can see, in fact, the comparison between this model and the previous one, the CFIs and the TLI, are actually a little bit higher than they were before. And then when we go down to the RMSEA, you see that it's actually 0. So, previously the RMSEA was 0.048, I believe, and now it's actually 0. So we actually do a better job of fitting our model when we were taking into account the measurement error. If we look at the estimates, you can see that in this case, really in large part, the unstandardized path coefficients were, pretty much in terms of significance levels, they're all, largely doing the same thing as they were previously. But we do have, again, more precision in terms of our estimates of the model parameters, because we have now adjusted those parameter estimates by correcting for measurement attenuation due to measurement error. So that pretty well concludes this discussion, and I hope you found this useful.